Hey, here we are to take a look at planar geometry with Gauss's law. Specifically, we're going to take a look at if I have a sheet that's a conductor this time. So like a metal sheet, okay? We talked in the last video about how we're not going to analyze this sort of thing for a finite sheet of charge, only for an infinite sheet. Or like a very, very large, we can approximate it as being infinite. So I've got a sheet now. This time, this isn't an insulator, okay? This time we're going to pretend this is a big chunk of metal, okay? It's a big metal sheet, an infinite sheet. And so the thing to realize about this, what makes it significantly different from working with an insulator, is that this will not have charge throughout it. If I charge this sheet up, where's the charge going to hang out? You say, at the outside surface. Now, there's no edges because this is infinite. The surface is just the top and the bottom surface, right? My charge will be spread out. And if it's infinite, then it's uniform. There's nowhere for the charge to gather. It's going to be evenly spread throughout over the top surface and the bottom surface of that conductor, okay? And now, side comment. Something that you may be wondering at this point is, what's the deal with calculating these E fields and stuff for these like weird shapes, for like a sphere and a cylinder and a sheet? This all seems very, what's the word I want? Like removed from reality, and this weird like freak special case stuff. Why are we looking at this? And the fact is that a lot of times we can approximate some other real shapes as being like these shapes. And you'll see at the end of this example a case of that. But also, there's devices that we're going to make and talk about in this next unit, capacitors, which essentially are formed from having a couple of conductors near each other. And we'll talk about ones where the conductors are shaped like planes, right? It's called a parallel plate conductor. We'll talk about a case of a capacitor where those two metal plates are cylinders nested in each other. Or we'll talk about a spherical capacitor where they're metal spheres. So it's gonna get used in the next unit, okay? We're gonna use this stuff. So like I said, everything builds off here, and this is important stuff to pick up. Okay, getting back to this. Okay, so let's go ahead, let's find, we're gonna do two cases super fast here for a conducting sheet, an infinite conducting sheet. So here we go. Again, planar geometry. Okay, this is going to be our case. Where are we on here? We did how many cases with a cylinder? Or sorry, with the insulating. I guess we did two, and I kind of talked through how we would do a third case. We did it for like if we want to have uniformly distributed charge in an insulator, if we're outside or if we're inside at some depth in the insulator. And then I talked about what we would do if the charge was some function of depth, of distance from the center. If the charge density was like that. We talked about how we would do that. Okay, but I didn't actually work it out, but it worked out enough that you can see. Okay, so now we're going to talk about a conductor. We're just going to do two cases, okay? We don't have to worry about charge. It's a conductor, so the charge is always at the surface. You ready? Real quick. Hey, look, it's an infinite charge sheet. Hey, what's the E field in the center, inside? Well, it's zero, of course. E is zero in a conductor at equilibrium, so that's done. We really only have one case to worry about, and that's finding the field strength outside that sheet then. So this will be quick. This will be quick. So here is, say, my conducting sheet. Okay, so I don't have to worry. Did I say insulating a minute ago? Here is my conductor. And again, this is an infinite sheet. Okay, and that does mean like the charge it's not spread throughout the inside. It's just at the surface, right? That excess charge would just be at the top surface and the bottom surface of this sheet, okay? I don't have to worry about there being, going to be evenly distributed, whether I'm not drawing this evenly or not, be evenly distributed on it. I don't have to worry about this edge because that edge is at infinity, and this edge is at infinity, and this infinity. So it's just spread out all over this surface and spread out all over the bottom surface, all right? So here we go. Let's see here. What do we have? We have an infinite conducting sheet. Fun fact, the thickness of the sheet doesn't matter for anything we do. Infinite conducting sheet. And what we're going to do is how much charge would it have? Well, an infinite sheet would have infinite charge. So of course we're going to talk about charge density. How are we going to describe charge density? We're going to talk about our charge that's on this surface, right? We'll talk about charge per square meter of surface, that charge on that top surface, okay? So we'll talk about it having a surface charge density. This is a true surface charge density. Sigma, okay? Again, that's like a Greek letter S, lowercase Greek letter S, sigma. That's terrible. It's a good thing you know what it says. All right? Okay. Okay, with this uniform surface charge density sigma, and we want to go ahead, find E outside, okay? Well, obviously, say write it down, E inside is 0. We got that, right? Okay. Find E outside the conductor. Okay, and we know that that field is just going to radiate out from the metal and radiate down from the metal, right, from that sheet. And inside in the middle here, E is 0. Okay, so we're trying to find the field out here. So maybe there's some point like right here, above it, I don't know, wherever you want, right here. Hey, how strong is the electric field there? And so you'd say, oh, well, I'll just draw a Gaussian surface. We use Gauss's law. Integral E dot dA, integral over closed surface, E dot dA is my charge inside over epsilon naught. Okay, and you say, well, again, I need a surface that's going to pass through the point I'm trying to find the E field strength at. Of course, true, anywhere outside has the same E field strength. And I need it to enclose some charge. So that surface is going to have charge inside, and I want to make sure I design this in a way that I can do this integral easily and simply, and that dot product easily and simply. And so you would say, well, that's actually going to be a pretty straightforward thing. I know I'm going to do a right prism that punches through the sheet. And you say, now wait, I actually have a couple of clever options. One is I can make a right prism that punches all the way through the sheet. So maybe I'll do it like this. And am I going to try to do perspective? So it's like, behind, and it's punching into the sheet out in the middle, And it's going through the thickness of the sheet, and then punching out the top. Does that make sense? So this is the part, did that look symmetric? I want that to be symmetric. That's in the middle of the sheet, so punching through here, punching through here. Okay, got it. Okay, you get this, right? Okay. I don't know why it looks like you got fatter there. There we go. Okay, hey, there it is. I could do it this way. Okay. And when I'm doing it, I can make it look nice and symmetric. Does it really matter? Could this be shorter than this here? It could, because it's the same field strength everywhere here and here. But in this case, but that's okay. So I can do it that way. Another clever way of doing it is I'm trying to find the E field here, say, at that distance out here. Although it's the same anywhere out here, but let's see, we're trying to find the E there. Another way of doing the same problem would be do my surface, and then check this out. It punches up in, and then it stops inside the metal, inside the actual sheet, because inside the E is 0. I don't have to worry about any flux to that surface, I just have flux to this surface to worry about. Makes it a little bit easier too. You can do it either way. I'm going to go ahead and solve for this way first. Okay, let's do it that way. Hey, do I have to worry about flux going out the sides? You say no, because my field lines are going parallel to that surface, right, the side of this cylinder, right, this right prism, but particularly it's a cylinder shape I drew, right? I have no flux out the sides. I only have to worry about flux up the top and up the bottom, okay? And so when I do this, again, we say, hey, that flux out the top, flux out the sides, and the flux out, the electric flux out the bottom equals Q in over epsilon naught. And you say, well, there is no flux out the sides because E is perpendicular to the area vector there. Okay, my area vector sticks straight out of my surface, out of my bubble, and the E field lines are making a right angle with it. Okay, nothing's punching through. Okay, now flux at the top, flux at the bottom. In this case, by symmetry, the flux at the top, flux at the bottom will be the same. Okay, same field above, same field below. It's the same area, same field strength. It's going to be the same. And so I recognize that I can just double one of these, right? So I recognize that these are going to be the same. Okay, by symmetry. So I just have to do one. All right, so I'm just going to go ahead and take this one and double it. Okay, double the flux through one because it's going through both. So what is that flux going through? This area here, right? So you say, oh well, I'll just go ahead and say that's an area size A. So like here's my area vector A sticking out, right? All right, the area of this is A. And so you say, well, what they told me here was sigma, my surface charge density. And so you say, okay, well, sigma, that's the charge per area. So sigma is charge per area. If I take, now let's be careful about this. It's my charge per area, right? And so the charge would be sigma A, right? All right. Wait, why am I doing charge in already? How did I get off track? I'm sorry, I need to finish up the flux. I apologize. My start, I'll finish it up. I'm sorry. Charge sigma A, that's going to be, no. We'll come back to this. Sorry, I'm sorry. Let's finish up doing this left side. How did I get off sidetrack? Okay, I want the flux to go to the bottom. It's going to be integral E dot dA, right, for the bottom. And I'm going to double it because I got flux to top and bottom. So E dot dA, you say that's going to be, the E field is uniform here, so that E is a constant. The angle for this one, when I do it, you see, well, the area vector is going down and the field's going down. It's going to be a cosine of 0 degrees. So that's just 1, right? And what's left is just the integral of dA. Well, that's just A. So this is just EA times 2. Okay? And on the right side now, I got the Qn over epsilon naught. Now we're talking about the charge inside. Hey, what's the charge inside here? Well, the thing to keep track of here is, remember, there's charge on the top surface of that metal plate, and there's charge on the bottom surface of the plate. I'm using sigma is Q per A, so sigma times A is charge, but remember, that's the charge just on the one surface. I've got two surfaces with charge inside my bubble. So when I go to do my Qin over here, my Qin is not going to be sigma A, my Qin is going to be 2 sigma A. Okay, 2 sigma A. Because I got charge smeared out on the, I got charge smeared out on the upper surface, and I got charge smeared out on the lower surface when I punch through that sheet. I'm punching through, essentially, it's a metal plate, but it's covered with a sheet of charge on top and a sheet of charge on the bottom. And each of these has a charge density sigma. And so I've got 2 sigma A's. Okay, so what's going to happen then? Well, good things, right? Okay, I don't know why I just did it like that. 2 sigma A over epsilon naught. And so you say, hey, the 2 and the 2 are going to cancel. And the A and the A are going to cancel. And what I'm left with is just that E is sigma over epsilon naught. And you may recall us talking before, list of things to know about conductors in electrostatic equilibrium. And one of them was the field at the surface of a conductor in equilibrium is sigma over epsilon naught. And there it is. Okay, field at the surface of a conductor. Okay, now hang on a second. We'll talk more about that in a minute. I got one last thing I got to show. What if I had done it this way? Well, if I had done it this way and made my boundary, my bubble, my Gaussian surface, so that it ends inside the metal, then I only am enclosing one bit of charge here where it punches through the bottom edge of the metal. It's not punching out the top surface, so I just have the one bit of charge there. But I also I don't have any flux going through this surface because it's inside the metal where E is 0. So I'll just have flux out the bottom. So if I did it this way, how would this calculation be different? I'd have no flux out the top because it's in the middle of the metal. I would have just flux out the bottom. So I wouldn't have this 2 there. This 2 wouldn't be there. But that's okay because on the other side, when I look at my charge in, I wouldn't have an upper surface and bottom surface of a charge. I'm ending in the middle of the metal and only have the bottom surface. So I wouldn't have this 2 either. Well, those 2 2's cancel out anyway. I'm going to get the same answer out. Sigma over epsilon naught. Okay. Final thoughts on this, okay? Final thoughts on this on conductors. It goes like this. We just found that the field that's outside of a plane of a planar conductor, that outside the field is going to be that charge density, surface charge density, over epsilon naught, okay? This is a more useful answer than it might seem at first because of this. You say, wait, it's just a special case. It's an infinite sheet of charge. How is this going to be useful? We live in a world where there's things where the shapes are like curved and stuff, right? But if this is my conductor, what happens if I zoom in on this surface? Well, now the picture is going to look like this, isn't it? And what if I zoom in, it's a little curved. What if I zoom in even closer? Now the surface will look like this, won't it? When I zoom in and zoom in again, eventually it's gonna look flat, right? Now, it's true that when I'm out here, I'm gonna see those field lines radiating outward, perpendicular to the surface, right? And the field lines spread out, so the field gets weaker as you go farther away and all that. But if you zoom in, those field lines will diverge from each other less and less, won't they? When I zoom way in, don't those field lines look like they're parallel to each other? And at that point, this would apply. So the point is, when I'm right up against the surface, it acts as if it was an infinite sheet. And the field lines would be parallel to each other, and this would work. But when I do that, the sigma, that's just the local sigma, the local charge density right there. I'll have different charge densities, different parts of this curve, right? It'll be like very little charge per, small charge density here, big charge density, which high curvature, right? You get charge concentrated. But the point is, if I know the local sigma, I can divide by epsilon naught and I get the E field right at the surface, right next to the surface. And that works for any shaped conductor in equilibrium. So I can always say my E is going to be my local sigma, as the value, right? Okay, I can get my E field of any conductor. All right, so it's a more useful solution than it might appear at first. Okay, and we'll be interested in this when we do some stuff with capacitors next unit. So that is the deal. All right, is there anything else I need to say about this before we end this? No, I think that's it. That's it. Hey, that's electrostatics. That's the electrostatics unit. Calculating electric field strengths, looking at forces on charged particles, moving around, using Coulomb's law and Gauss's law. That's it. And this is, like I said, this is like the foundation we build on. Okay. So I know that we're going to spring break, and you want to, have some downtime. I get it. Finish up this homework set on this last thing. It's worth the investment, the time that you invest in it, because we're going to use it over and over again. But have a great spring break. All right. I know you'll get time to rest and hang out. It's just do a little bit of time of physics here. I recommend at the start, and then take a break. Come back and we'll be looking at charges and energy. We'll look at charges moving, electric fields getting pushed along by the field and gaining energy, getting faster, and look at kinetic energy and gravitational and electrical potential energy calculations. It'll be good. All right. So see you next time.